Hello everyone, and welcome to this session. Here we're going to build on our lecture about inferential statistics and on the lecture about hypothesis testing by introducing the method of analysis of variance, or ANOVA. The ANOVA procedure is used to decide if a significant difference exists among the means of different populations. These could be, for example, outcomes generated by different treatment combinations in an experiment. Now, we already compared means of two populations as part of hypothesis testing. We did this using a z-test when we knew the variance and a t-test when we did not. But we only did this for two levels. For example, when we wanted to compare a sample from a new process or a sample from a new supplier to the existing process. And we wanted to know if the difference between the means was significant. Then we were able to perform either a z-test or a t-test. However, an ANOVA, and specifically a one-way ANOVA, can be used for evaluating the difference between means for more than two different levels, more than two different populations or groups. A two-way ANOVA is also important because then we can compare the significance of effects in our designed experiments, where we have two different factors at two different levels. For this lecture, however, what we want to understand is when an analysis of variance procedure is used, and we want to be able to list the assumptions needed for an ANOVA. So just as a short recap, recall that we learned how to test hypothesis for means of a normally distributed random variable. We had three practical scenarios. So here, case 1, case 2, and case 3. We were checking if our mean for the new process, for example, is less than, greater than, or not equal to a hypothesized mean, which we called mu0. And that could have been, for example, the mean of the production population that we know. And then we would compare our new mean against that. Now, again, just what we did was we compared a test statistic against a critical value, so that the probability of our type 1 error occurring is contained within a specific small value alpha, which we define. And remember, type 1 error would mean that we would reject the null hypothesis. And in all of these cases, for the null hypothesis, we assume that there's nothing's changed, that the mean of the new sample is the same as the mean of the regular population. And we have to then prove beyond reasonable doubt that our new mean for our new process or new supplier, for example, is greater than, less than, or different. And then we did that by keeping our alpha values small. Now, if we knew the variation, the variance, we could use z as our test statistic. And then this test statistic would relate the sample average for the new process to the population mean, and we would then check that z observed value against the critical value. Likewise, if we didn't know the variance, we would take the sample standard deviation and calculate the t-statistic. And so the t-statistic, again, it has n-1 degrees of freedom, and there again, we would see if our observed t-statistic was in the critical region, and then we would say we would prove to this alpha level that our new population is different than the original population. So now, what happens if we have more than two populations, more than two groups? And here we have some sample data. This is very old sample data. We were checking the length of the gates in transistors, and this is quite old now. So these this is actually a slightly different measurement. It's not actually the gate length, but it's called the gate bias. But it's a small length of polysilicon that we were measuring, and we were looking at different processing conditions for DRAM production. And actually, what we've shown here is a cloud of data here. A cloud of data. We're actually comparing two different values. And we're plotting then this nested value, one of the values for process 1, 2, 3, and 4. And this actually was the process of record, the process that we were currently running. And our value, you can see here's a box plot with the data actually superimposed on top of it. And the colors, you can see also by this cloud of all the data together, the colors are indicating then the different processes that we use. And if you can see just underneath, there's a box plot under each one of these here. So we're showing here kind of the descriptive statistics here with the box plots and showing some data and how you can plot the data. Now, question is, are the means of these different populations different? Here we can see population 1 has this so-called GC bias here about -60, while for the other distributions they seem a little bit higher. So now I was trying to find a good way to show this. So this is not perfect, but let's turn this data on its side. Okay, so let's rotate my graph this way, and I've kind of stretched it out a little bit. And what I wanted to show you here was, say, I look, for example, at my group 1, my process of record, using red here. I could also draw not just a box plot, not just the raw data, but the normal distribution, the model of that data. And if I changed colors, for example, to blue, and I looked here at this population here, this blue population, this is not accurate, obviously, but you could draw also then the normal distribution for the process number. There's 1, and here's process number 3. So the question then becomes, is the difference between these two means significant? And we want to also then compare, is the difference then between the other means? Are they significant? When you have mu3, for example. So I've drawn this on the next slide a little better. Again, not perfectly accurately, but what you can see here then is if you can take the data, as we've done all along, we can calculate the sample average and the sample standard deviation and use those to model the normally distributed data. We assume here normal distribution, and we need to see if the means are different. Now, we've done this, right? We've looked at two different populations before. We've looked at, for example, comparing two different means. And we've done that, and we could do that also then for these two. We could do it for these two. We could do it for these two. We have lots of ways of comparing means, right? And so if we did that when we had mu1, mu2, mu3, mu4, and mu5, you could compare all the different means. And you could do this, with using our two-sample t-test, which we've already done before, and we would test the statistical difference between the means of each of these groups. Now the problem is that the number of t-tests will increase the more groups you have, and the more the number of analyses, just as we did way back in course 1, the higher then the probability of committing a type 1 error. For example, if we set our alpha value to a nice value like 5%, and if we compare these 5 different groups like what's shown here, we'd end up with 10 pairs of tests. So 1 to 2, 1 to 3, 1 to 4, 1 to 5, 2 to 3, 2 to 4, 2 to 5, etc., etc. And then we would only have this is going to be 0.95 to the power of 10, gives us about 60% chance of not having, of accepting the null hypothesis of not having a type 1 error, and that's not acceptable. Just performing t-tests ad infinitum is not going to help us. So what we need here then is an ANOVA. So the ANOVA, or analysis of variance procedure, is used to decide if a significant difference exists among means of populations of outcomes generated by more than 2 combinations in an experiment. And so for this reason, an ANOVA is extensively used for analyzing data from experiments. And we'll look at that specifically in the lecture on two-way ANOVA. And what we want to show you next then is how we would do this for a one-way ANOVA when we have only one factor that we're comparing. So just to summarize, for 2 or more groups, the ANOVA method will test differences between means for normally distributed variables. It will identify then significant X values and give the best X value or the best treatment that will give you the most favorable response. So it's an extension of the t-test. And actually, an ANOVA with just 2 groups is mathematically equivalent to a t-test. And for the ANOVA, we're going to use a new statistic. This is called the F statistic. And the F statistic is used to compare the variance of the populations. Now, important assumptions. We are assuming for the ANOVA that the populations are normally distributed. We are also assuming that there's a homogeneity of variances, meaning that the populations all have the same standard deviations. We're also making sure we're taking simple random samples, and the samples should be independent of one another.